All right, we're going to go ahead and get this thing started. Hello, everyone. Welcome to the DNS Track. My name is Duane. A lot of you I know were in the DNS-OARC workshop the previous couple of days, but for all the new faces, thank you for coming. We hope you find all this material interesting. We're here for a couple hours. We've got 6 presentations, and we're going to start off with an introduction from Mr. Keith Mithcell to tell a little bit about DNS-OARC. So here's the clicker. This is a sensitive area, so try not to jostle too much. Yeah.
Okay, this is going backwards. Okay, good afternoon. I'm Keith Mithcell, OARC President. We've done something that we've been kind of wanting to do for a while over the past few days, which is, as well as having a OARC workshop back-to-back with NANOG, actually doing a bit of coordination on the content. So most of the presentations you're about to see are actually a reprise or shorter version of material that we had presented at our workshop over the past 2 days. So if you find it interesting, would just like to tell you a little bit about OARC, and maybe this is something that is relevant to what you're doing. So what does OARC do? Okay. We're basically here to act as a focus, non-profit neutral membership organization to facilitate coordination within the operators that are focused on DNS issues, and also to work with the research community. And there's various ways that we do that. We facilitate research, we do software tools, we help to build community relations just like NANOG does, and workshops, and also just trying to distribute clue and do education. We've been trying to explain this a little bit better for people who don't necessarily get all of that on the first pass. And we think we're a little bit like a library. We have a huge collection of data, but we don't just store the books, we make them available, we perform scholarly analysis and research on them. More importantly, we facilitate others to do that. And we have a Friends of the Library program where you can give us money to facilitate all this, and also get access to events like our workshops. Here's all the usual suspects in the DNS world that are members. This isn't a completely exhaustive list, but it's all of them up until a few months ago. You can see there's a lot of CCTLDs in there, there's a lot of GTLD operators, there's address registries, there's vendors, there's ISPs who operate large recursive resolver farms. Data gathering is a big part of what we do. We also have various tools for member-only sharing of information, so that if there are strange things which are impacting your infrastructure, there is a chance to discuss these confidentially without necessarily tipping off the bad guys that you're onto them. Governance, well, this is all kind of cookie cutter stuff within the industry now. We're a 501c3 legal entity registered in the US, trading in California. We're doing about 600 to 700K of annual revenue, and that's done on a sustainable basis. We have neutrality and self-governance. We just had a board election from among the community. And for various services that we do, we contract a number of staff who perform, like myself. In fact, all but one of them are here in the room. So if you want to talk to us, we're available. We also have a program committee. 2 of the program committee members are sitting here, which is how we achieve the coordination. And they're doing some really awesome work within the program committee in terms of getting the content that we have at the workshop. So what have we done this year so far? We hired a project development manager to get involved in more activities in terms of developing tools and services. We've been doing big data for over a decade now, and the good news is that's a lot cheaper and easier than when we started. So we've been adding storage capacity. Our main data set is over 80 terabytes. We just added a record amount of 9 terabytes to it. We do this thing we call the day in the life of the internet every year, where we collect data from authoritative servers for 48 hours and add that to our archive. We also did something new. The root operators of publishing data about their operations to a standard RSAC 002 that's been created by RSAC. They're all publishing that independently. What we're doing is collating and gathering and archiving it in perpetuity. I'm pleased to say we've made good headway in terms of growing our subscription revenue from members, and also, I won't quite say booting out the freeloaders, but certainly cleaning up some of the legacy participant categories that we have. And we've also started charging a small amount to cover our costs for workshops. It's cheaper than NANOG, but obviously we would like members. This is a benefit that you have if you're a member, is to send free delegates to the workshop. If you've been thinking about OARC membership in the past but thought that's too expensive, we have a couple of new membership categories. If you're doing things that contribute to research and understanding of the DNS, then maybe you're an academic, you might want to consider a supporter membership. And we've also got a new entry member category, which is only $1,000 a year, but it's limited to individuals or small organizations. So we just had our fall workshop, as Duane mentioned. 25 presentations. We had about 40 submitted, so the 25 is the good stuff. You can see all the slide decks at our meeting site, which we're also putting the slide decks for this track on. The videos are already there. Dave Knight did an awesome job webcasting it all, so that's all on YouTube if you want to see any of the presentations that you missed. And we had 130 attendees. A big thank you to Sierra as our local sponsor, and for the social. Nominum also sponsored us, and we like to work with other events such as NANOG, and NANOG's always great for helping us out with connectivity and other aspects. As I said, we had board elections. Congratulations to Paul as our newest board member, and also to Dave and Duane who've been re-elected. This is a staff, as I say, all of us except William are around for the next couple of days, so please do come and speak to us if you want to know more about OARC. So technical stuff. We have quite a lot of physical infrastructure. We have various reasons why we need to continue with physical rather than cloud infrastructure. We recently upgraded it to 10 gig. Having said that, the physical infrastructure that we have is going to have to be moved. So we're working on a plan for that, and we'll certainly be talking to members, colo providers and other parties about the hosting that we need to replace our existing equipment. We've also just started running a mailing list for the ICANN CCNSO SCCIR group. So that's something new that we're doing. And we've also been looking at some trust group platform as a way of providing more vetted and secure communications and relationship management amongst our members. So that's it. I mean, that's my vegetables. You can now get on with the technical meat from the other presentations. Happy to take any questions. One of the things that we do with our workshops that our members have expressed a strong preference is that we co-locate NANOG, ICANN, RIPE, IETF meetings. So our next one will be with the IETF, first time we've been to South America and Buenos Aires. In a year's time, we can't get the members to decide whether to come back to NANOG in a year or whether to co-locate with the ICANN meeting. But we'll certainly, we were with RIPE in Amsterdam earlier this year, and we'll be going back there in spring 2017, and highly likely that we'll be co-locating with NANOG in 2 years' time. Happy to take any questions, or happy to follow up with any of you after the session. Okay, thank you.
Okay, thank you, Keith. So our first presentation today is from Brian Summers, who's going to tell us how his company handles certain DDoS attacks. Looks like you started in the middle of your talk or something. I don't know what's going on there. All right.
It's the best place to start.
So this may or may not work. This works. Trying not to touch that.
Okay. Hi, I'm Brian Summers. I work with OpenDNS. I'm a site reliability engineer, so we're responsible for maintaining the DNS infrastructure, getting configuration changes out to it, and developing it to deal with operational issues and other projects within the company. I've always been interested in the networking side of software. I've worked in software for 28 years, more years than I care to remember. But ironically, my current job working with DNS has a big effect on the network, so it's probably quite appropriate to present here. So I'm going to talk about DNS denial of service attacks. Most of them are Yep.
Okay.
Is that better? Yep. Is that better? Yep. So I'm going to talk about denial of service attacks. Most of them are distributed, but not all of them. So the first and most simple type of attack is the accidental attack. It's when people have something misconfigured, might be sending the same query over and over again, or it might be a misconfigured development box looking up localhost because it lost the content of Etsy hosts or some such thing. There are amplification attacks, which are kind of old school these days. We don't see, well, maybe we do see them, but we don't care about them that much anymore because we seem to have them nailed. This is where the source address is falsified, and they send a small query soliciting a big response. Usually it's going through a domain that the bad guys own, so the bad guys will pre-set up record responses of certain sizes to try to get the maximum response size out of the resolver. So they might set up a record with a response with 1,000 bytes, 1,024 bytes, 1,500 bytes, 2,000 bytes, 4,000 bytes. Most recursive resolvers will give you answers up to 4K if you send an eDNS buff size option. So they'll have these answers pre-prepared. They'll falsify the source address in the DNS query to be the guy that they want to attack, and they'll send queries as fast as they can, and then we send responses. They don't care whether the response is in the cache or not. Their desired result is that we send answers to the target of the attack. And then we've got our NX domain attacks or our random label attacks. These are the most difficult ones to deal with. So they usually target what looks like an authority. They're actually targeting the IPs that are nominated as the name servers of their domain that they're attacking. So usually, again, the domain will be owned by the bad guys. The bad guys will point their name servers at the guy that they don't like, and then they'll send lots and lots of queries to us for that domain with random labels at the start of the queue name, which means that we haven't got them cached. We send our queries upstream, and to us upstream is the IP number of the target. So the target gets lots and lots of queries. So the first two types, the accidental attack and the amplification attack, are reasonably easy to deal with because the source address is constant. It stays the same throughout the attack. It's not falsified, so we can just limit the responses that we send based on too many queries from one source address. To do this, we have lots of metrics around each query that we receive. So our metrics would include counts around the number of A records, the number of quad A records, MX records, etc. But also metrics around the response sizes that we're delivering back to the clients, and whether or not they're a customer, what class of customer they are. We count all of these up. We have different rate limits for each of these numbers, and when they exceed the rate limit, we stop sending the responses. If they continue to persist with the attack, then from second to second we reduce their limits by 10%, which means that after 10 seconds of sustained attack, the limit is now equal to 1. So they could be sending us 10,000 queries per second, and we're actually responding to one of them. And it's very convenient in this case because certainly in the case of the amplification attack, the attacker doesn't actually know that we're not sending any responses, not unless he has some way of monitoring the target's network. The random label attack needs a little bit of a kind of step back. So in order to identify a random label attack, what we're currently doing is we're leaving it up to our big data systems to be able to correlate the data and tell the resolvers when there's a random label attack going on. Our big data system gets query logs from all of the resolvers. They all feed into the big data system. And the big data systems will identify when it starts to see a huge number of domains being responded to with negative responses. So there have to be 500 unique domains queried under a given zone, which is unusual in itself. But if 95% of those responses are negative responses, and again 30% of those negative responses are serve fails, then this looks like an attack. So it figures out what the longest domain name satisfying all of those criteria are, and it classifies that as an attack. And then it does one of three things with this information. So the first one is the easy thing. If the domain in question has less than 100 queries, or less than an average of 100 queries per hour over the last 2 weeks, then we just drop the data on the floor. So the big data systems feed the domain name back to us. We put it in a drop list file, and that drop list file is squirted out to all the resolvers. The resolvers honor it by matching the domain name as it comes into the resolver and just dropping the data on the floor. However, of course, if we have a domain name that's a little bit more popular than that, then nobody's going to appreciate all of that data being dropped on the floor. So for domains between 100 and 500,000 queries per hour, we behave slightly differently. We put it in a different list. Our resolver is full of lists of domains that we need to behave differently for. But this list is a freeze list, and the idea behind the freeze list needs another step backwards. I'll explain how our cache works. Our cache isn't a kind of ever-growing cache. It's a pre-allocated cache. Most of our resolvers currently just allocate 10 gigs of memory for the cache. And the cache has a head pointer and a tail pointer, and the head pointer chases the tail pointer through memory. And every time it needs more space to put stuff in the cache, the tail pointer consumes the oldest record, and the head pointer then gets some more space to store some new stuff. The 10 gig cache that we have on most resolvers will last for about a day. So the records that we put into the cache tend to go into the cache and stay there for around about a day. When we look the cache up, we have a queue name, we look in the cache, we find the best or the most recent queue name entry. And if it's in TTL, then we have a record that we can respond to the client with. If it's not in TTL, then we have to go and do an upstream lookup. So at any given time, we'll have a series of records that we'll have a match for a queue name that may or may not be still within TTL. So going back to the freeze list, the way we manage the freeze list is if somebody sends us a query that matches the freeze list and we find that queue name in our cache, whether the queue name is in TTL or out of TTL, we'll treat it as a valid query. And if it's out of TTL, we'll go and relook it up upstream, and we'll give the client the answer. If it's not in the cache, then we don't. We drop it on the floor. Which means that the domain that's suddenly under attack will still respond to things like www.domain, but we'll stop responding to things like randomlabel.www.domain. And this generally works. There are a couple of other kind of aspects of this, like when we recycle a resolver, it will come back up and the freeze list won't be activated for 5 minutes after boot time so that it can see those records. But it does mean that attacks will leak through, so to speak. So to give you an idea of what sort of data rates I'm talking about, or at least proportional data rates, so this is a dropped graph. It graphs all of the data that we're dropping on the floor in the recursive resolver. The pink or the magenta here represents the data that's hit the drop list. So of all of the data that we drop, you can see that most of it's drop list data. The yellow that skims across the top there is rate limited data, and then the blue spikes are freeze list data. So stuff that was more active domains that we saw these random label attacks coming through. And to put that dropped data in perspective, the green stripe here is the dropped data, and the purple piece on top of that is the queries that we're responding to. And most of our resolvers have graphs that look very similar to this. And for what it's worth, the blue at the bottom is error responses, so garbage domains, malformed packets, that sort of thing. So you can see that at non-peak times we can be dropping up to 40% of our traffic just on the floor because it's dropped data. We see very few false positives. We believe it really is just garbage data. So one of the other things that we do, which isn't strictly speaking a denial of service attack, in that we're not being used as a vehicle to attack somebody else, but it's possible that we might be accidentally attacking authorities through our misbehavior. And this can happen if the authorities stop responding to us for some reason. So as a recursive resolver, somebody asks us a question, we go to the authority, we get an answer, we keep it in the cache. We serve that record out of the cache as much as we can. When the RTT runs out, or when the TTL runs out, we query upstream again. If the authority doesn't respond, then we send the query upstream and we wait for a while. And then we time it out, and then we query upstream again, and we wait for a while and we time it out. So the semantics or the timeouts that we use in terms of looking up a given queue name against an authority has suddenly changed from whatever the authority's TTL is to whatever our timeout is. And that's a surprising thing for authorities. And if authorities have mechanisms in place to see this happening, they might decide to firewall us. So we want to become good citizens and try to avoid that happening. So there are lots of steps that we take, but I think it's easier to explain with a graph if I can find the graph. My graph isn't here. Okay. I think this is an old slide deck. Okay, so I'll explain it manually then. So I had a small table of with name servers going across the top, left to right, and timeouts going down the side, top to bottom. And how our resolver deals with things is it will take the name servers for a given domain and it will shuffle them and it will lay them out left to right. And then it takes a fixed set of timeouts that it will lay out bottom to top, is how I like to see it. And then it basically goes through the resulting matrix and queries each name server with a given timeout, and if it doesn't respond, it goes on to the next one, and wanders all the way up the matrix. When it runs out of boxes to query, it returns serve fail to the client. So what we've implemented is a mechanism, if you can picture this matrix that we're going through with timeouts down one side and name servers across the other. We remember the round trip times that we got responses from the authorities on a per IP and per queue name and per queue type, per IP, per zone and per queue type basis. So we remember the round trip time, and if they don't respond within the timeout that we're querying, then we put them at the top of that timeout, go on to the next one. And we remember those round trip times for the next time we query them. So as a result, if 2 of the 3 name servers for a given zone are a little bit latent, if they take 2 seconds to respond, or if they take 0.8 of a second to respond, then we're going to query the 3rd name server in preference to those. And if one of those name servers is taken out of service, if it's rebooted, restarted, its anycast goes away or whatever, then we eventually push that name server, assuming that we don't have other name servers to kind of stand in for it. We push that name server off the top of our graph or of our matrix. And when things fall off the top of the matrix, we put them into a 40-second timeout. So we just stop querying them altogether. And the net result of this is that an authority that reboots all of its name servers or loses net connectivity or loses the ability to respond to us will get a flurry of queries, and that flurry will then peel off quite rapidly, and then they'll start getting single queries to each name server every 40 seconds until the problem's solved. It's easier to explain with the other slide. So this is the exciting part of the talk. So when I did this talk on Sunday, I hadn't got a very good story, because on Saturday night I'd looked at the graphs and decided that my story wasn't correct. Since then I've been worrying about why my story wasn't correct, and I have come up with the reason why it wasn't correct, and I have a better story now. So these graphs represent a NX domain attack, or a random label attack. And what tends to happen with these random label attacks, it's as if the bad guys have a fire hose, and they decide that they're going to target person X. So they turn on their fire hose and they point it over here, and they're looking at person X, and then they turn it and point it at him, and then eventually turn it away. Or in this case, what it looks like happened, if you look at that top graph, you can see the attack start, everything's fine, nobody's upset with anybody. And all of a sudden we have this huge magenta block appearing on our graph, and that magenta block is representing dropped data that has appeared in our drop list. So there's been some sort of a random label attack, and it's pointing at somebody that we know is being abused as a random label attack, and we've decided to drop the data on the floor. Now this goes on for 4 hours. So they're pointing their fire hose at these people for 4 hours, and we're just dropping the traffic on the floor, and nobody has noticed. None of the other graphs are demonstrating any sort of misbehavior, so it's just a completely new fire hose that's been pointed over here. 4 hours later, all of a sudden the drop list data completely disappears. So it looks like they've turned the fire hose, and they're now pointing at somebody that is not in the drop list. And in fact, this attack was against a domain name called okcoin.com, which is a Bitcoin company. And I was a bit confused here, because the drop list disappeared, but why weren't they added to the freeze list? okcoin.com do about 2,500-3,000 queries per hour or per 10 minutes, a reasonable amount of traffic, so they should have actually appeared in our freeze list, but they didn't. There was no sign of them in the freeze list. What actually happened here is it seems that many of these Bitcoin operators have a way of communicating payment details via DNS wildcard records. So I did find one of these DNS wildcard records on a domain just by spending a lot of time Googling things earlier. But these wildcard records, if you abuse them and start sending random label attacks at them, well, guess what? Every one of them is responded to. We'll never see negative responses, and as a result, you'll never, or the domain will never get into any of our drop list or freeze list. So what actually happened here is that the random label was under one of these wildcard domains, and as soon as they turned that fire hose on okcoin.com, okcoin took it on the chin. So that second graph here, you can see the red, which represents serve fails. So this is a huge number of serve fail responses. The green is a bit of mitigation if we have a facility where our customers can opt into, instead of receiving a serve fail, if we've got an expired record in our cache, then we'll serve them the expired record. So some people were getting some old data from okcoin.com during this time. But in all likeliness, some people that were getting that expired data were actually the random source IP numbers that were being pumped into these denial of service packets. So nobody was actually getting anything. So looking at the third graph, you can see just for reference that the salmon color across the top perfectly reflects the serve fails. In fact, it's measuring the same metrics. But the other non-zero R codes, so everything except a zero, were pretty much the same. Yellow is NX domain, and the very thin green stripe across the bottom of that graph is other things like form error and all of the other responses. And just to see the full graph, so this top graph here is again the traffic graph. The purple is our regular responses. And you can see between those two arrows, if you have a reasonable imagination, you can see that there's actually a layer of stuff on top of that graph, running along the top of the graph, that can be described as, given that it's a stacked graph, as the green traffic and part of the blue traffic along the between the two arrows. So it looks like all of the additional traffic that we received was just additional traffic, so it wasn't existing traffic being treated in a different way. And then looking at the middle graph, it's again a kind of revoicing of the same data. The brown stuff is serve fail, the yellow stuff is oversized rate limiting. So we rate limit large packets slightly differently. I guess part of the responses that we were receiving were classified as larger than normal. And then the final graph is kind of more interesting to me than anybody else, in that this is a graph that represents the number of context slots that our resolver has internally. So we pre-allocate context for client queries that we receive that we have to remember when we send queries upstream. The green is the pre-allocated context slots, and the blue is the ones that are in use at the moment. So as you can see, we had an awful lot of stuff to remember during this. We oversized the green so that we can deal with denial of service attacks. And this sort of thing also causes big CPU spikes in terms of CPU usage, etc., that appear in other graphs. I'll talk a little bit about future technologies. There's a few things that I'd like to improve about our drop list and freeze list. I guess our freeze list is the big candidate. The idea is that we can provide thawing within that freeze list. So the green text there represents what we currently do. So as I described before, if stuff is already in the cache, then we respond to it, even if we have to go upstream to provide that response. So one of the enhancements that we could do is, if we see the same question coming in more than once, then we should, rather than dropping the second duplicate question, we should actually send a TC as a response. And if we send a TC as a response, then a good citizen will query us over TCP, we'll believe them, we'll go and fetch the record, and we'll then have it in the cache so that they can query us again. This would be ideal. It's a little bit tricky for us to implement that, but it's not impossible. So that's one of the things that I plan on working on in the future. And of course, when we do respond to those TCP requests, we'll probably, after sending the answer, close the TCP connection immediately, just because they weren't people that really wanted to talk to us over TCP. They're people that we made talk to us over TCP. One of the other ideas was to do what our big data systems do in terms of correlating or identifying the attack. So to be able to identify the attack, we could actually store metrics in the cache at the level of the zone cut. So where we cache the name server record, we could actually pre-reserve 3 counter slots in there. And the counter slots would probably need a little bit of additional information, like the second to which those counts apply, so that we can roll over properly from second to second. But if we could identify the negative responses that we're sending for a given zone at different levels, then we could probably fairly easily identify a random label attack at a given level in the zone, and then start dropping them ourselves. Okay, I think this is just about the last slide. And another very obvious improvement that we could make, at the moment our freeze list doesn't have any concept of labels that are normal labels. So for example, if you put mydomain.com into our freeze list, well, that just means that www.mydomain.com, if it wasn't queried, will not be responded to. There are lots of kind of normal labels that we could put into a list, and even if it's hundreds of labels big, then it would be the obvious right thing to do. And going back to caching the negative responses at various different levels, we could also apply the whitelist to those negative responses, so that we can so that we can not treat those well recognized domain names as negative response candidates. I think that's about it. I haven't got my ending slide either, which gives you these IP addresses. So if you're interested in talking to OpenDNS, of course, we have a free service, so it's you can talk to me. So that's it.
So we've got about 4 minutes for questions. Any questions for Brian?
Donovan from Amazon. I was curious because it looks like everything you mentioned was mostly volumetric-based attacks. Do you see anything like a complexity-based attack, like a different cost for resolving different types of R codes or labels, or like something like a nonsense length and a delegation chain that you have to chase down? Anything like that?
We do see queries like that. I mean, that's part of doing business, I guess, as a resolver. So we have various mechanisms in place that make us not really care too much about that. So for example, if you kind of get caught in a loop kind of pointing back at yourself somehow through something that we haven't otherwise identified, we keep counts of how many times you've been through the resolving process as a query. And when you hit, I think it's 350, then you're thrown out. So you can actually spin and use some CPU, but you eventually get thrown out. Similarly, if you have a delegation that has a delegation that has a delegation, I think we'll have 5 levels of that, and then you're out. And we keep metrics and all of that stuff, so if we see any spikes in those sorts of graphs, we get interested. But otherwise, there's usually a kind of certain level of noise that we essentially ignore because we see it every day.
All right, thank you very much, Brian.
Thank you.
Next round up. These are all. Yes, so next up is Ray Bellis from ISC, who's going to be talking about the F-root research he was doing.
So you just see my slides?
Yes, read fast.
Hi, I'm Ray Bellis from ISC, having joined there back in May this year, having spent the previous 7 odd years at the .uk domain registry. So, very shortly after I joined ISC, I was asked by our operations director, Jim Martin, to have a look at our F-root deployments with the aim of looking to see where we might put new F-root nodes. First decided that before I could actually even think about where we might put new nodes, that I needed to study what we have out already and see how our existing nodes are working, and see whether there might be any changes we might need to make there anyway. So I decided first of all to look at using the RIPE Atlas probe system. Are there people here not familiar with RIPE Atlas probes? Okay, who here has got a RIPE Atlas probe? Okay, that's good. hopefully there's somebody at the NANOG meeting actually giving away RIPE Atlas probes, but for those of you not familiar, they're tiny little Linux devices that you can just plug into your network, and they form a very, very large distributed network of network monitoring probes. And RIPE have something like 7,500 of these deployed globally, although they are concentrated in Northwest Europe, as you'll see shortly. Fortunately for us, every RIPE probe has a built-in measurement that is free of charge for us, where every 4 minutes they go and ask every root letter, so A through M, what's your host name, using the shown hostname chaos query. And our servers will respond back with a host name that indicates the nearest IATA airport code, so in this case AMS for Amsterdam, 1, we actually only have one site in the Netherlands, and A that indicates that it's the A node of a dual node pair. We also of course get the latency of the queries. And with this data and access to the RIPE APIs, they have their own built-in visualizations on the RIPE website that you can look at. But I wasn't quite happy with what they would actually visualize for us. I needed the ability to filter based on our known sites and also look back historically at the data. And at the time, the RIPE APIs weren't quite as up to date as they are now. So I built our own internal tool using a load of JavaScript coding and OpenStreetMap to build some new graphs. And this is an example of what we get out. Each dot's an active Atlas probe. Fairly obviously, the colour denotes latency, with the red being quite bad latency, typically 200 milliseconds plus. It should be noted that the Atlas probes are typically found on end-user sites, so the latencies I'm measuring here do tend to include whatever local loop is present between the end site and the rest of the internet. So it might be a DSL line. If you're lucky like me, you've got 1 gigabit fibre to the home, so it's not so bad. But generally, it still gives a fairly good picture. The difference just between a diamond and a square on this is simply whether it's the A node or the B node at a particular site that we've hit. So, having built this tool and also looked to see what my own connectivity was providing, the first thing we found when we were looking at our Atlanta node was this, that practically every node that was hitting our Atlanta node was actually in Europe. This was not good, for obvious reasons. The latency that we were offering to those users is a lot worse than it could be. And notwithstanding that there are 12 other route operators, my philosophy on this is that we should all try to be as good as we are. And despite the fact that the way the DNS works, that the servers will tend to try and pick a server out of, that has a decent response time, nonetheless, sometimes they'll always come back to our server, and having a 200 millisecond latency for these people to have their DNS resolution done is not good. It turned out this is actually just down to a very simple misconfiguration on some of our network connectivity. There's a large global tier 1 that we peer with in many locations, particularly in Europe, but we also happen to take some management transit connectivity from this provider in the US. And essentially, unbeknownst to us, on the 3 sites that we connect to them in the US, we were publishing the FRoute prefix, the /24 prefix that we have there. And they were treating that as a transit route, a customer transit route instead of a peering route, and therefore gave it a higher local pref. And that essentially meant that anywhere in their global network, if they saw our prefix, they would route it all the way to Atlanta instead of to the nearest peered node that we were operating. This is not good. So it was fortunately a very, very simple configuration change on our routers to remove that prefix from our peering sessions and our management sessions with them in the US, and the result was this. Okay. Fortunately, well, Europe's fixed. That particular node doesn't get that much traffic anymore, but at least it's not doing any harm. With the tool, we can also see when people leak our routes unexpectedly. The FRoute architecture comprises 5 global nodes where we announce a /23 prefix into the global routing table. I should say this is all for IPv4. IPv6 is somewhat different. And we have 50 odd local nodes that only advertise a /24, and it's exported with a no export community on it, and that's only used at local internet exchanges. So in this case here, what we've seen is we found with the tool, at least temporarily, there was a leak where a Chilean ISP had not honoured our no export community and was advertising our route to a whole load of ISPs that they were affiliated with in Italy and the Balkans. Fortunately, again, this is fairly easily fixed. Conversely, no export can also work against you if people do the wrong thing with it. The Polish IX appear to have a misconfiguration where everybody uses multilateral peering via a root server, and the root server itself was honouring our no export community. So, unsurprisingly, none of the other peers on that multilateral peering system could see our routes. I'm not sure how this one got fixed, but it did get fixed. And the result was that suddenly all the rest of the ISPs and the nodes in Poland could see us, and indeed, in fact, even some west there in Germany. So that was, again, far better for that community because they were now actually able to see their local node as they're going to one in a different country or even, worst case, a different continent. So another issue that we have, and this is actually still outstanding, but you may have noticed when I showed the big global map at first that showed all nodes that there was predominance of red in northwest Europe, particularly in France. And the issue we have there is it's a certain French telecom operator who has a interconnect with us in Palo Alto. They used to have a peering session with us in Paris, but they dropped their connectivity at that particular IX. With that being the only remaining connectivity in Palo Alto, the net effect is that every user of this ISP, many of the downstream BGP peers, and this includes, for example, there you might see just under the hook of Africa, a lot of the ex-French colonies that ended up connecting back to this French operator. They all long haul all the way back to Palo Alto. So many of these are getting 200, 300 millisecond plus latencies all the way back to Palo Alto, and instead of, again, using a much more local node. Show you some examples here of what happened with another operator who was in a similar position, in fact, where, again, they would have a single interconnect. So toggle back to and forth, you can see what's happened where when I drop the interconnect, when I drop the prefix from the interconnect to the Palo Alto site, suddenly a whole load of nodes in Europe and even Eastern US and Africa are now going to a much more local site again. Here's a close-up view of the situation in Europe, where our Amsterdam node is very busy. It's a global node, so it's actually announced as a /23 to the global routing table. Now, with the Atlas probes being distributed by RIPE, they are typically very highly concentrated in northwest Europe. They're very freely given out at RIPE meetings, so there's thousands of them in that area. In fact, of the 7,500 live Atlas probes that I routinely get data from, probably about 2,600 of them are routinely picking the Amsterdam node as their preferred FROOT instance. But what's almost more interesting on this graph is not what's there, but what isn't there. You might observe that there's nothing in Spain, or almost nothing in Spain, and absolutely nothing in the Czech Republic. So you might think that may mean that the Czech Republic's very poorly connected. In fact, it's the converse, because that's what happens if you look at our Czech Republic node in Prague. It's incredibly well connected within Prague. It's so well connected that they have no need to go outside of the country for connectivity to other FROOT instances. So that works very well for us. It happens that the Prague node also serves the rest of southeastern Europe fairly well, we're very pleased to see that good a centralised local clustering around one of our FROOT instances. That's one that's working very, very, very well for us. We have another slightly interesting one here, where in the Ukraine we again have a lot of nodes inside the country connecting to there, and a few up in the Baltic states, but perhaps surprisingly, or perhaps not surprisingly these days, with the political situation between Russia and Ukraine, there are no nodes in Russia talking to the Ukrainian POP. So it's clear that geopolitics can sometimes have an effect. Although I don't have a picture of it, we have a very similar situation with our node in Tel Aviv, which unsurprisingly doesn't serve anybody outside of Israel, because none of the rest of the Middle Eastern countries appear to want to actually interconnect with the Israeli sites. And that's it for the pretty pictures. If you have any questions, please shout up. Okay, easy crowd. I had 15 minutes the other day when I did this one. Okay, sorry, Duane has a question.
I'm coming to this mic because when I hit that mic up there, it caused a loud noise last time. So, Ray, my question is, Are you making these tools available for other people to use?
Yeah, we're looking at how we can do that. I mean, the code currently isn't really very well parameterized to allow for the variances between how different root operators name their nodes and how you identify which node is in which city. I mean, my code has been written so that if I know that AMS is an IATA code, then I have a database for IATA code, so it automatically puts the dots in the right place.
Yeah.
So if you have different naming conventions and also different architecture, so if you only have local nodes or only have global nodes, it would need a little bit of twiddling with code to sort that sort of thing out. But yeah, we'd be very happy to consider that.
Excellent. Thank you. Anyone else?
Hello, Javier Angel, RIPE-NCC. Actually, among other things, I'm in charge of Atlas project, so
Lovely.
if there is any questions or anything, I can help. About the code, we have a very active actually community around the open source pieces of the code. On the GitHub, if you search for RIPE-NCC Atlas, you will see the GitHub repo. And yeah, please don't worry about if it's not complete or not parameterized, because as soon as we commit, resources within RIPE-NCC as well as a lot of people from the community will work with it, and they will make it.
Yeah, I mean, the root op community has a newly standardized YAML file that describes root instances. Unfortunately, not all the root operators are providing the same information yet, so the froot YAML file says what the latitude and longitude is of every node. Other operators aren't necessarily doing that, but it would be great if we could simply just read in that file and have it run for every froot node and produce the graphs we need.
The reason that I brought this up is because actually we have a hackathon right before RIPE meeting in Bucharest in 4 weeks, and actually that would be something that some people might pick up during the hackathon to improve.
Yeah,
And one last correction, it's at the moment it's 8,784 active probes.
yeah, I'm only getting the data I need from 7,500. I'm not sure where the other 1,000 have been lost.
No, but yeah, we are expanding as fast as possible. So.
Yeah.
Cheers. Thank you.
Thank you.
Great work. Thank you.
Thanks, Ray. Thank you. So next I'd like to invite Eddie up. He's going to talk to us about the mysteries of eDNS, I believe. All right. You can use this if you like. Yeah.
That is the end again.
Somebody
Yeah, no
make sure all
worries.
the slides work.
All right. So, hello everyone. First, I'd like to just take a moment to thank OARC, because long ago, when I was like a real operator where people would page me when name servers broke, that entity that I worked for used to send me to NANOGs, and it was in the mid to late 90s. And usually at NANOG at that time, when I don't know, there'd be like one 30-minute DNS session or something, and that was always like, yeah, that was always the highlight for me. So if you find yourself with the same affliction as myself, or find yourself with the same affliction that I have, you may want to attend an OARC meeting. So thanks for the great program you guys have. Okay, so eDNS. So we are in the DNS session. By the way, I'm Eddie Winstead. I work for ISC. I'm one of Ray's co-workers. And this is, I'll use this. Okay, so we're in the DNS session, but we're talking about, my topic is eDNS. Okay, so the DNS protocol is actually over 30 years old. So this is this speaks volumes to its success and what it was able to accomplish as far as the original protocol design. But of course, the internet has changed in this 30 years of time. Okay, so one of the ways that the DNS has been extended is by eDNS, the extension mechanisms for DNS. One of the things that you're probably most familiar with is that in the original design, the maximum DNS message you could send me over UDP was 512 bytes. That has been extended to 4096. So why do you want eDNS? One reason, of course, is what we just talked about. You know, when these things were designed, eDNS, by the way, is over 15 years old. So it was all assumed that in 2015, certainly all of us would be using IPv6, and we would all have deployed DNSSEC, right? Oh wait, it is 2015. Yeah, okay. Anyway, so DNS response sizes are much larger these days. But with eDNS, the nice thing is it's a hop-by-hop extension. So if I'm a recursive resolver, say, and I want to ask you you, the authoritative server in question, I can advertise to you that, hey, you can send me back data over UDP up to 4096 bytes. So that's pretty cool. All right. Some of the more recent ones are client subnet ID. These are used in the content delivery networks to essentially identify where a question is coming from and hopefully send you to the data that you asked for in a better way. Okay. Another one that is sort of in the works now is DNS cookies. I say in the works now, the drafts have been around forever. We have sort of an initial deployment of DNS cookies that is in bind 9.10. However, this is a compile time option. Okay, so it's not on by default. However, in bind 9.11, we do intend to turn on DNS cookies by default. So this stuff is coming. More extensions are coming. And whatever else the next great thing in the DNS is. All right. So why are we seeing some problems? The main problem that we're seeing these days is middleware, particularly firewalls. You know this, firewalls do funny things, right? Sometimes we ask them to do funny things. Sometimes they do things that we didn't think we asked them to do. Anyway, so if you're entirely blocking EDNS zero traffic via a firewall, this is indistinguishable from packet loss. So in terms of in terms of the effect on the DNS ecosystem, this is bad, right? Because to borrow a term that Mr. Houston uses a lot, the DNS is very obsessive compulsive, right? We just keep asking questions over and over and over. That's what we do, right? The joke was that he was referring to Mark Andrews, who also works for ISC. Since a lot of you don't know him, I excluded the slides of the DNS cop. But if you ever want to know who the DNS cop is, you know, it is Mark Andrews. Okay. Right, exactly. Well, yeah, that's because Mark is nicer now. He gives you 30 seconds instead of, yeah, exactly. So anyway, Mark is really hot on these DNS cookies, right? This is one of his things that he's doing. So we deployed a tool over a year ago, and we've been doing some test data on EDNS zero compliance, and that's sort of the whole point of me standing up here. But anyway, one of the major problems is that you could actually mess up DNSSEC validation, okay? If you're actually doing it, right? You could mess it up. And then again, why I'm here is, you know, these new technologies are coming out, and we want name servers to be able to take advantage of them. So again, firewalls do crazy things. These are some of the things that we have seen based on our testing. One of the most interesting ones to us was this response to unknown DNS options. We've actually seen some name servers that serve authoritative signed zones, and they respond to unknown EDNS options with a form error, which means I don't do EDNS. So if you're a client and you want to validate the domains that they're serving, you're going to have a problem. So this is the website that you can visit to actually run the tool, and I assume maybe some of you will now. So here it is, and I'll get back to this in a second. I'm actually going to do a quick demo going against conventional wisdom. But so the nice thing, I said, we've been doing this for over a year now, so there's actually some historical data out there. So that's really interesting to take a look at. So some of that is, so here we've graphed that roughly, you know, we've had really pretty good success with having servers being EDNS aware, okay? But we really fail, I'd say it's a pretty good failure when we're in the 60% of full compliance with EDNS 0, okay? Again, at this point, this isn't the DNS server software. All the vendors that I know of are doing the right thing. It's more in the middleware boxes. The other fun thing about historical stuff is you can actually see events. This is one day Amazon decided to remove. They had previously been blocking EDNS1 or not responding to EDNS1 requests. EDNS1, of course, is not a valid. There is no EDNS1, right? But you're supposed to respond back with bad verge. They were actually not responding. So the nice thing is you can see sort of jumps and graphs, and you can sort of pinpoint like what happened on those days. So that's very interesting. All right, what can you do as a network operator? Well, I highly encourage you to, of course, check your own authoritative zones. So check those. If you see any issues, the tool is actually really handy in telling you why those issues might exist and what you might need to tell either your firewall vendor or whoever is responsible for why you're seeing this behavior. Yeah. So with that, I will do a very quick demo. Good, yes. So here's our site. If you want to know more about eDNS, we have some links in here where you can actually, it takes you to the RFCs about eDNS 0. If you want to find out more about cookies, we have a link there as well. But the main thing to show you is here. And of course, I'll test us first. It isn't really fair because we knew it was coming, right? And Mark works for us, so this is an example of what you should see. And this will take a little time to go out and do all the queries. I suspect we might be getting some other traffic out there from you guys, so this is good. All right, so that's good. The other nice thing is there's this a link provided here at the bottom that you can go back and review this report in the future. So if you go make changes, you can retest and refer back to your old reports. All right. So you remember that employer that I told you about that sent me to a lot of NANOGs? Well, I don't want to publicly shame anyone for having eDNS 0 problems, but I'm going to publicly shame them. Actually, they're experiencing an IPv6 routing problem right now. Okay, so I get to use that as a way to have a test that doesn't shame someone. So all looks good with their name servers, right? And assuming they didn't fix it today, and they have not, good, we will get a failure. Because, of course, if I'm getting no response, then to me that looks like you're failing all these tests. While we're waiting for this to finish, I will say that all these tests are just digs, okay? We have some funky options that we're doing with some of the digs, and if you want to take advantage of those options that we're doing in your own test, you have to have dig version 9.10.3. All right, so we got some timeouts. So to the tool, it looks like this is a failure, right? So, so if I look at this one, you know, this was a test for unknown version handling. What we expected back again was bad version. We did not see that, of course, because we got nothing back. Okay, so if you're seeing this sort of thing, then you just click here very handily, and the DNS cop has a link for you, and will tell you why you were doing things wrong. Okay. So I do want to point out right quick some of the historical data. If I go back, if I do this takes a little while because it has all the data in there, but this also has all the dig commands that we run for the test. So if you want to do these manually or just do some testing on your own from the command line, which is what a lot of us like, that's there for you. And then you can see some of the historical data that we're seeing. Okay. And with that, I'll take any questions. Okay.
It's from OpenDNS.
There you go.
Oh, it's getting better. It would be nice if you had an option to remove the plus no recurs option in that web page. I tried to test our resolvers and...
Ah, okay. Duly noted. I will take that back to the powers that be. Yeah. When you were talking about your freeze list, by the way, I was thinking maybe cookies may help you out. I don't know. We'll see. All right.
Thanks a lot.
Thanks, everyone.
Slide deck. All right, right, last up is Tomek Slavicek, who is from CZNIC, who's going to be talking about benchmarking.
Thank you very much. Hi, my name is Tomáš Hlaváček. I'm from CZNIC, which is CCTLD for Czech Republic, Europe. And I'm going to report on our effort in benchmarking of authoritative DNS servers. On contrary to what you might expect, it's not about the CCTLD operation. And don't get me wrong, we are very serious about our CCTLD, but actually the motivation for conducting benchmarking or starting this effort was that we have our own authoritative DNS server called NotDNS, and we committed to sort of benchmark-driven development process, which means that we needed to define some benchmarking package or create some methodology for acquiring data and processing them. And that's what I'm going to talk about, which means that I'm not going to brag about our numbers and that stuff, but I would like to spark some discussion about our methodologies and see what opinions you might have about it. So, what do we have? We have, of course, data acquisition system, which means that we have some hardware, few servers connected through 10 gig network, and we have a software package that's based on Distel. And you might know Distel because it's old, or it has been presented few years ago on DNS-OARC or maybe somewhere else. We took that package and customized it pretty heavily, but basically still it's a software that contains automated measurement system, which means that it builds the software from different sources like Git or Tarball or something like that. It sets the server environment, meaning that it deploys zones and creates files with queries that we are going to bounce off the server during the measurement. And of course, it does the measurement, and I'm going to discuss it on next slides. How do we measure and what do we actually do? And of course, we do some slight post-processing inside this software package, and we create inputs for our statistical software, which allows us to see some interesting results afterwards. So there is one particularly interesting piece of software inside the package, and actually it's the query generator, because we need to generate a lot of queries and send it to server. So for that we use TCP replay software, and it's really interesting piece of software because it uses NetMap kernel API, and this API claims to be wire speed capable, which means that it should be able to send theoretical maximum of 14 point something millions of packets per second, but actually with DNS queries, which are bigger, it means that we can send something like 5 or 6 millions of queries per second from single server. But actually, downside of this software is that because we can also throttle down the sending performance, or the output performance, because we do a lot of tests on lower speeds than the maximum. The throttling inside the TCP reply causes bursts, and we devised that we can overcome this by using more sources. In our case, we use 2 sources at lower speeds, and then the packet flow is much smoother, and it's simply better. So regarding the variables that affects the results, of course it's hardware and operating system, and of course version of operating system and libraries and everything. And saying that, I have to say that it's heavily dependent on tuning of operating system, which means kernel, TCP/IP stack, network interface card drivers, and that stuff. And actually, we have a script which is a part of the package, so you can, if you download the package, you can see the all tuning we does we did for the operating system, like pinning threads to CPUs and do some fancy IRQ binding stuff and setting TCP/IP stack inside kernel, everything. Another factor, which is perhaps the most important, is actually the DNS server software, which we are trying to measure, or the performance of which we are trying to measure. And of course, it depends on dataset type. We have a lot of dataset types, like 15 or something like that. And the idea is that each dataset type should resemble or should represent some type of DNS usage, like root zone or CCTLD, or hosting of a huge number of small zones, like what hosting providers usually do. And of course, we have non-DNSSEC versions of those zones and DNSSEC versions of those zones, which means that we can measure differences among them. And another thing is that the performance also depends on a number of queries that are actually asking for existing domain versus non-existing domain, which means that we can also measure different portions of those queries, and we took what we thought that it's representative for particular dataset types. And of course, it's all these things are part of the software package, so you can download it and examine it if you want. And in the beginning, in the end, I'm going to have a link to the website which contains results and the software, or link to the software. Regarding results, what we usually get is a vector or series of numbers that actually represents the number of answers that we got for a particular measurement at a defined speed. We usually start at 100,000 queries per second, then 200,000 queries per second, etc., up to 1 million, and we have a percentage of answers what we got from the server, so we can plot it and see what we have. Actually, another text slide before the actual results. It's about the benchmark-driven development process. We are actually not there now, because now the idea is that we would like to measure each version in Git, or each master version in Git continuously, and the benchmarking should be a part of our code review process. But actually now it works like that. We semi-automatically measure only the versions that we really need to understand, and it's usually when we deploy some experimental features or experimental development methods, like we tried different compilers or different compiler versions. We've tried feedback-directed optimizations and different configurations for auto FDA in GCC. And of course, we measure internal data structures and changes in internal data structures, or methods for manipulating them, which is really interesting stuff. We also put a huge effort into measuring different network interface cards. And on last DNS-OARC, one of our colleagues presented results, like we had comparisons of I don't know, 4 or 6 different network interface cards in different server systems, which was really interesting part of that work. So, speaking of results, what we usually get is charts like this one, and by the way, this is a chart that shows three measurements, three randomly picked measurements for two versions of not DNS. The first one is older one, which doesn't have socket option reuse port feature turned on, and which is the green one. And another one is a newer version with this feature committed into the sources. And as you can see, there's no doubt that this feature is really helpful, and that the red line is really better. So it's really simple to tell. But there are not so obvious situations like this one, and once again, this is comparison of the same not DNS version on two operating systems. The first one, the green, is Linux, and the red one is FreeBSD. And if you look at this figure carefully, you can see that the red measurements are somehow more displaced, or that there is a bigger variance in FreeBSD measurements. So and actually this is only random pick from or randomly, those are only randomly picked measurements from bigger sets. So if we look at the complete result, which is this one, you can see on the box plot that FreeBSD is really hard to understand, and actually it's not easy. The question whether Linux or FreeBSD is better is really not easy because of variance on the right side of the chart. So we concluded that we need some statistics, and actually the reason for thinking about it in more formal ways or in more mathematical way was that we actually came to things like this, which is visualization of three different versions three different versions of Knot that actually uses three different compiler options, or three different compiler settings. And actually developers asked me which one is better. So if you can, or maybe you can see that maybe the red set of options is slightly better, but you can really tell, you can't really tell because it's, you know, crowded with measurements and points, and the variance is quite high. So in order to answer our developers, we thought about it, and the obvious idea was to use hypothesis testing, and luckily there is a test that pretty much fits us, and it's Hoteling's test, which is sort of, or it works similar, whatever. It works like t-test. Which means that you can decide whether a mean value vector is the same among two groups of measurements, and of course your goal is to disprove that, but the downside is that we need the same variance in both sets that we are trying to compare, which actually worked for this measurement, or this measurements, but it's not obvious, or you know, you have to prove it before you can use this test. So another option is to use linear model. So we devised linear model like this, and again this is quite dramatic version, because on the right side the downslope is usually not that steep. It has longer tail, but this is the basic idea that the absolute number of responses is linearly or is linear in terms of queries per second to some point when the server gets saturated and it starts dropping packets or dropping queries, and since then the performance goes down. So actually the linear model is like this, or this is the mathematical expression of the same thing. And the good point here is that we can use standard methods like analysis of variance to find significant factors, meaning that we can do a lot of measurements with different tuning or different small changes, and then we can pick the changes that really make some significant difference among the measurements, which is really good for both for tuning of the measurement environment as well as for tuning of the actual software. And another interesting test is Starkey HSD, which means honest significant difference test, and it allows us to prove that some group is different from another's, which means that if we think that we have some best version of software or best version of compiler settings or something like that, we can really prove it by using this test. And there is another thing that we are now researching into, and it is estimating the breakpoint, which means that we can estimate this the position of the breakpoint on x-axis, which means that it would be one integer, so it's easy to compare, easy to think about. But where I am, oh, whatever. It's easy to reason about single integer, but the implications are that we are losing a lot of information, so it's sort of in progress work. Latest addition to our effort is testing of DNSSEC or impact of DNSSEC on node DNS as well as on another authoritative servers. And actually the DNSSEC adds more variables to the tests, because you can choose the algorithm for signing, you can choose NSEC or NSEC3, and of course you can choose the number of queries that actually allows DNSSEC to, or allows responses with DNSSEC included. So we concluded that actually the average response with DNSSEC is something about 370 bytes, which is quite high, but and it actually limits the theoretical performance to 3.3 million of packets per second. But actually, our data sets are a bit extreme in this. So you can, or if you think that this is not representative, we can create another data set and test it, because it's quite easy in our environment. The first measurement of DNSSEC on not DNS was pretty scary, because the results were like this one, and this is the comparison of NSEC and NSEC3, and actually the NSEC3 was better. So we digged into the source code and did some optimizations, and after that the current version looks like this. So it means that the red and green lines are almost the same, and technically speaking there is no statistically significant difference among NSEC and NSEC3 now in KNOT and in our measurements. But actually, still there is a huge gap among the DNSSEC enabled measurements and the blue line, which is or blue lines, which represents the measurements without DNSSEC. And we are looking into this problem now. Actually, from what I have seen, there is some gap in all DNS or in all authoritative DNS server implementations that we have tested. So maybe it's a problem or it's not only our problem, but it's sort of feature of all implementations now. So, what are we going to do in future? We would like to add more automation into the system. Actually, now it's all shell scripts and Python, and the interaction among servers is done via SSH, and we are thinking about using Ansible instead of those ancient tools. And we would like to add new data sets, especially for DNSSEC, or especially because of DNSSEC. And we would like to measure TCP, because people are now discussing DNS over TCP as a default option, and actually the performance is the most important issue there. So and it's actually quite a challenge to measure TCP and do it right. So it's on our roadmap, and we would like to add more comprehensive results to the website, because now what we have there, it's those are only processed charts. Like it's usually the mean value from 10 or 20 measurements, but no box plots. So it's it's easy to read, but it's not that scientific as it would be. And as I said in the beginning, we would like to spark some discussion about DNS benchmarking. Actually, as a matter of fact, there is a DNS benchmarking mailing list in DNS-OARC.net domain. So we would be happy if somebody reached me or us through mailing list or personally, or whatever you find fit. So that's it. Thank you very much for your attention. The results, or the web page with results, is here, and there is actually a link from this web page to sources, so you can browse through them and see whether you like it or not. If you have some questions, I think I have some time to answer. Yeah. Okay.
Questions for Thomas?
Okay. Thanks.
Our last presentation today is from Ariel at ICANN, who's busy having a conversation in the back. It's your turn, buddy. He's going to talk to us about rolling the KSK at the root. Oh, I don't know if we have the other. All right. Okay.
Disclaimer, I'm not Jeff Houston. Okay, so my slide is not there, but basically what the ICANN slide was about is mainly what ICANN is doing about the key rollover, and also for the replacement of the HSM. There are two processes in which ICANN is involved right now. So the first is the key roll, but at the same time, because some of the HSM has been in operation since 2010, and there is some issue that has been identified with the battery lifetime on those HSM. They are using the same occasion to also replace the HSM. So the slide was about the process that is being used for the replacement of the HSM. Most of them are done at the same time as the key sign key ceremony that you know about. The 21 and 22nd ceremony was used to do that. But for the key roll itself, it is a more it's a process that has a more wider impact, because that go into the whole integrity of the DNSSEC process, and specifically for the root zone management. So for that, there has been a lot of consultation on this, and an external design team has been put in place for the key role. Well, how do we do this to be sure that it doesn't impact the whole integrity of the DNSSEC system? A document has been produced by this external design team. Jeff is part of that, and the comment period for that document is still on till I think 8 today, Montreal time. So I will encourage you to read it, and if you still have comment, to quickly provide them before the end of the comment period is very important, because the input from the community is key on that. There has been several consultation around this already, and this is the last phase, I guess. I'm proxying Ed Lewis here. I'm just in charge of technical engagement at ICANN. Sorry. So his team and few other at ICANN are heavily involved in this whole process, and the key role aspect of this may sound, very straightforward for anyone that know about DNSSEC and everything, because we do it at the different level. But when it comes to the zone file, to the root zone file, it becomes a little bit tricky, and there is a lot of attention that need to be given to that. That's why the wider consultation was put in place, and that external design team was also put in place to make sure that all the different aspects are taken into consideration, so that the process of rolling over the key does not impact everyone. I'm sure that the slide will be put online for people to look at, because Ed sent it this morning, I think. There was some confusion.
Yeah, sorry about that. The slides that IDL was supposed to present are on the DNS-OARC Indico website, so they can be downloaded there on the day for the DNS track.
Okay, wonderful. Thank you very much. So just speak without the slide. Then I will let the real Jeff Houston to probably present his slide. Thank you.
Who did that? Yeah, right. I'm Jeff Houston. I'm a member of this design team that ICANN pulled together to do what? This design team to actually look at the issues around rolling the root. If you were paying attention as Adiel was speaking, you would have seen these roll through. And if you're really good at multitasking, I'm just going to repeat what's already there. So I will do this relatively quickly. Why is this important? Because oddly enough, while IPv6 has been a little bit of a disaster on the internet, DNSSEC has been one of these overnight successes. To be perfectly frank, around 80–85% of all users, when they do a DNS query, actually ask for signatures. Most of you turn on the DNSSEC OK bit. That's phenomenal. 1/3 of you actually start looking at the keys that get returned and figure out whether you like it. Around about 15% of you, if you get a bad answer, will live with that and go, I'm not going there. The rest of you go, what's this serve file nonsense? I'll just go and use a resolver that doesn't do validation. Naughty people. But that's a lot. And actually in North America, it's even a lot more. Predominantly because of ComSec and Google's public DNS, around 20% of folk here in this area, Canada and the US and other bits and pieces including Greenland, 20% of you actually do full-blown validation. If it's badly signed, you don't go there, which is really an amazing number. Interestingly, on weekends it gets higher. which I think is a bit of the Comcast issue. Corporates don't, Comcast does. So why is that relevant? Because we're going to do about as big a damage as you can possibly do. There is nothing worse than this, because there's no plan B. When you roll the root key, that's it, right? So this is one of these things about, you know, we're going to destroy an awful lot and we're going to do it really without an awful lot of knowledge about what the consequences are going to be. ICANN took this very seriously, and the issues around signing the key took a long time to come, and back in 2010 it got signed with a lot of fanfare. Now 5 years ago out came a practice statement, and the practice statement said, and it's circled there, each key signing key will be scheduled to be rolled over through a key ceremony as required or after 5 years of operation. Now if you take this as a serious contract between sort of the root key operators and the world at large, something's just gone a bit wrong by about 3 or 4 months, because it was meant to have happened a little while ago and it hasn't. But the commitment's there, and certainly it's time to figure this out. We are not talking about the key that signs most of the root zone. Because if you're one of those folk that pore over zone files, and I'm not one of them, I'm not obsessive compulsive, or at least I'm not as obsessive compulsive. Most of the stuff is signed by a zone signing key, and that zone signing key is regularly rolled. That's fine. The DNS key part of the root zone is signed by the key signing key. It signs across the zone signing key, and that's the key that has not changed in 5 years. That's the one we're going to change. So most of the time that's kept offline in these highly secure facilities with attack dogs and floodlights and all that kind of stuff. Of course the West Coast has a more relaxed attitude, and we found one in Amsterdam, cleverly disguised. And George Michelson, my colleague, who is definitely into KSK spotting, has found the hidden mobile unit sheltering in Montevideo. It's moved on since then. Who knows where it is now? So the cast of actors inside this are the root zone management partners, which is ICANN, the NTIA, and VeriSign, and I'm part of a 7-man design team. This has been talked about for some time. I mean, there's been a lot of talk. 2012, 2013, a study by the Security and Stability Advisory Committee in 2013, and this design team worked this year. So this year, this design team has been talking, pondering, talking, doing phone calls at midnight, thanks Ed. 2 a.m. sometimes, thanks even more Ed. And finally, a report has come out. It's in that URL there. Comments do close on the 5th of October. Is that today? Oh, okay, move quick. There are only 6, so if you come up, you know, you'll be heavily featured. And from these comments, we'll prepare a final report. We'll then pass it on. So, every resolver that asks authoritative has a problem, because the current key they're using is not going to last past a roll, right? So if they're doing validation, they need to do something. They're going to have to load a new key signing key. So there are 2 ways of doing it: an automated way, or with people like you. Plan B, people like you, is the problem, because you're the problem. Now, we've tried this in the past before in various other ways, and in theory the route is pretty similar to other things, right? You use the new key to sign the old key, you publish both of them, you withdraw the old key, you go to the pub and everything's just fine. And this is the kind of model that we're talking about. So you publish the new key for basically 1 quarter. You don't use it, it's just part of the DNS key set signed by the old key. You should be paying very careful attention at this point. Very, very careful attention, because your resolver needs to pick up the new key value. Because according to this approach, on the first day of the next quarter, no matter what the day of the week, on the first day of the next quarter, I'm not sure what time, by the way, you might want to ask them, they're going to flip, withdraw the old key, publish the DNS key set signed only with the new key, and press bravely on. So that's the time of the switch. Can I get rid of that stupid nonsense? I can. God, as soon as I do that, wow, this is stuffed, isn't it? View. We'll try again. Full screen. Right. That critical switch on the first of 1 quarter, whatever time zone, I assume it's probably Eastern Standard, but there's a sort of a grace period where we haven't revoked the old key. So if the world falls apart, you know, you guys all complain or something terrible happens, there is a period where we can back out of this. But at some point, planned 1 quarter later, if everything goes okay, the old key will be republished with that bit set that says, do not trust this key forever. If you've got a record of it in your resolver, destroy it right now. That's the revoke bit. This is no longer useful. And at the same time, the zone signing key keeps on changing every quarter up the top there. Our experience has been pretty crap. This is one that dates from a few years ago, where every time the RIPE NCC changed the key, this is before the root got signed, the amount of traffic they were seeing went up by a factor of 10 and never went away. Because this is obsessive compulsive behaviour. As soon as the resolver found that it couldn't validate the answer, it just asked more things and kept asking and asking all the way down through all the various NSs. The more NSs you had, the worse the problem. It's an interesting comment about the DNS itself. How many NSs do you have? How many do you need? Less is better. Okay, so that was then. This is now. We've learned so much and everyone runs recent code, right? You're all keeping up. Everything's just happening perfectly, isn't it? Crap. I still see A6 queries. I don't know about you, but there's some awfully weird stuff going out there in the DNS land. You guys really run Model T DNS sometimes. So there are two kinds of real problems out there. One is you're not going to pick up the new key, and that's a disaster. Or the other one is during that phase, there are some times when the responses get bigger than normal. Now, a normal response is around 900 octets for a tell me the DNS keys, but sometimes they're going to get higher than that. That 511 one is a problem. Do you run managed keys? Can we tell in advance if you're not? We can't. Now, I'd really like to say, you know, it's because we haven't looked. We've looked under almost every single rock, and the way the standards are built, and you know, between RFC 5011 and RFC 4035, there's just no way when you get the two keys out there, you can tell which key the resolver is using as its trust point. You can't design an external test that a resolver can betray itself, because it'll always trust the old key because it's there. So even if you're not following the role, you'll still say things are fine. This is a problem. So when we roll the keys, it's a leap into a dark for this. Okay? So like I said before and I introduced, there's a lot of DNSSEC out there. Rolling the key is critical for a lot of you, more than you think. There is a real issue about V6 and response sizes, and when the response size gets above 1280 in V6 in DNS, there are some folk who really don't like what they're seeing. However, no one uses V6 in the DNS. Might be a good thing in this particular case. Less than 1% of the queries I've seen in various tests actually use V6. You could change protocols, and about 80% of the folk who like, you know, normal old RSA actually understand ECDSA, which is really good. The other 20% don't give serve fail, they just treat it as unsigned. So Cloudflare has now gone using entirely elliptical curve cryptography, and in theory you could contemplate this. The good thing about this is response sizes are small. The bad thing is if you want to change the key and change the signing protocol, that's two balls up in the air at the same time. You might not want to juggle that much. This is the DNS response size. Even at 1300 octets, around 6% of resolvers don't like it. They will give you small eDNS0 buffer size, they'll back off to TCP. The TCP load at the root will rise as a result of this. But when we looked at .org, it was running 1650 octets in its response, and no one's complaining that .org is broken. So maybe response sizes aren't as big a problem as we thought. I've just said we can't measure 5011, and that's bad. So when we roll the key, we're just not sure. There will be a bunch of folk who won't follow us, a small pool of users, and we have no idea. That's the way it is. There's the public comment, there's the comment closed, please read and comment. But I want you to take very careful attention to the next two slides. Good dog. Bad dog. If you've got that, you've got a problem. Now I don't know how many of you have got that. But if you've got that, You've got to make sure that in that quarter, when the new key is published, you manually add things, because no one's going to do it for you. Only this one will do it for you. So this, we're all happy. That, I hope you're looking, because no one's going to look for you. That's sort of where we stood. Questions?
Warren Kamari, largely with a rant. So there's a public consultation period open at the moment, and it closes sometime today. This is a very scary, very big change. There've only been 6 comments so far, and this scares me a whole lot because, as everybody's acknowledged, some amount of people are going to break, and we have no idea how many. We hope it's fairly small, but we don't really know. One of the issues which I think we have is simply outreach. The document suggests that, let me find a little bit, there should be outreach within technical forums such as those at which the original deployment of DNSSEC in the root zone was presented. I don't think that's nearly big enough. Since we did that, we've had a lot of presentations at, OARC, NANOG, the public DNSSEC workshops, a bunch of stuff in the press, etc. There are thousands of people who are running this who have no idea that they have DNSSEC validation turned on. There's a bunch of CPE that's been deployed that does this. There's been a bunch of OS deployments that have this turned on. And people simply don't know that this is happening. And so at some point, the key's going to roll, and they're just going to fall off the internet, and they're not going to know why. And at that point, they can do one of 2 things. They can turn off validation, which seems like a bad idea if we actually think DNSSEC is useful, or they could all just point at, validating resolvers run by someone else, which also kind of seems like a bad idea, potentially. So I think that the outreach really needs to happen a bunch more. I think that there should be a greater acknowledgement that we're just jumping into this blind. And I'm kind of concerned at how little sort of panic there is over any of this. One of the other scary things is, in 2013, there was a lot of public consultation, there was a lot of feedback received. SAC 63 was published, which had a whole bunch of recommendations, and if you look at the document which was produced by the design team, it's almost exactly the same as the recommendations in SAC 63. They're reworded and moved around a little, but between 2013 and now, almost nothing seems to have happened, and it's really kind of scary that we're getting to this point. If we had started trying to do instrumentation a couple of years ago, maybe we would have some visibility. I don't really know why I'm ranting at you, because I'm largely saying things that you're saying. Mainly, I would like the rest of the community to be paying attention, to raise the whole, oh my god, something bad might happen here flag, to tell the rest of your friends that if they're doing DNSSEC validation, they should figure out if they're going to survive this. Tell your friends, check to see if you're doing DNSSEC validation. Please, people, pay attention.
Yeah, I'd agree with what Warren said. 5 years was a contract, not a commitment. The key isn't going stale. They've actually replaced the batteries on the HSM. That will be okay for a while longer. You can, as a community, say back to this public consultation process, why are you leaping off a cliff of unknown height with unknown damage? We, as I said, have no idea how many bad dogs are out there. You could ask for more time, and we could do work in standards bodies and with resolver vendors to actually expose resolvers that behave like this, of folk that are keeping their resolver code up to date. There is a possibility of doing more work if you don't feel that it has to roll right now. But we've got no comment back on that. Why now? Well, because there was an original commitment 5 years ago. Why ever? No key is eternal. At some point in 2115, we'll think, only 2,000 bits? You're nuts. At some point the keys have to go. So why now? Good question. Why not forever? Can't do forever. But between the two, there's probably more leeway. So, you could gain time by changing resolvers in the meantime to understand a little bit more about the size of that cliff. Yes. So, Warren, I agree with you completely. But, like all of these public processes, if you're expecting that design team to be the font of all wisdom about rolling keys, I think you're kind of expecting too much, certainly of me. I think there's more wisdom out there than there is in my head. So, you know, say something.
Yeah, I think the ideal the conclusion of what you just said is the key, and that's why we are having this presentation here, to make sure that people understand what is coming up, and also picking it up and share it with other. What I wanted to say as well is for the report of the design team, the comment period has been extended already once, and if we need more extension, probably we need to speak up so that people who want to comment, if there is any comment, to do that. But the more important is for people to understand that something is coming down the road, and they need to pay attention to what is coming on. And if you have suggestions about that, I think we'll be more than happy to take it up.
So let me just do this quick poll. How many folk run recursive resolvers? Okay. How many folk know what kind of key you have, managed or trusted? How many folk have trusted, not managed? Right? And that's the ones that know what they're doing. This problem is actually quite widespread. It is a conservative view of security to use trusted keys. That's a fine thing to do, but the obligation of you and the folk that use your resolver is then to track this stuff extraordinarily closely. And if the person who set it up resigned and worked on another job and left you with a legacy and you have no idea what's going on, you're going to be a victim. And at this point, we have no way of understanding that. Theoretically, we could use time productively. There are ideas about how to measure, but if the idea is roll now, 2015's moving on, it won't happen. So if you want us to do a little bit more work, if you want the community to think about that, go there and say, take some more time, measure some more, understand this a bit more. If you think it's fine to roll on, it'll roll on. But, tell us. That'd be really helpful. Any other questions?
Warren Kumar again. I guess I'll just quickly clarify. My pissiness is not with the design team doc, it's with the rest of the system and the lack of attention.
Oh, go for the design team doc as well. I don't care. Fine. Okay. Oh.
If there's time, that's fine. If not, okay. Hi, I'm Chris. I work for Google, but that's not who I'm saying this for, because they would be upset, maybe. Why did we not change this key more often, more earlier in the process? Like, we would have figured these problems out when DNSSEC did not matter. I realize revisionist history is super great for everybody, but maybe with the next one of these things we could learn a lesson and not wait until everybody cares.
Why was section 4.5 of RFC 4035 written precisely the way it was, that we couldn't delve in and find the trusted keys you're using? There's a whole bunch of these, if only 20/20 hindsight. And I agree with you, leaving it for 5 years and then bringing it up as a problem and ignoring it until then, it's not quite that bad. I think the work started in 2012. But it is certainly...
Haven't rolled the key yet, have we? I mean, we're not going to really find out what's broken until somebody changes it, because...
Well, again, this is this issue about whether it is possible to gain deeper insight into the number of folk running trusted keys. And there are ideas around that if we had the ability to change resolvers.
How much naval lint do we care about?
How much, sorry?
Naval lint. I mean, my problem is, yeah, we can't get this data. We could sit and think and think and think and think and think and think, and then 4 more years will go by. But, like, we know we have to change the key eventually. Start changing it now. Every month, change it.
Welcome to the design team internal conversations. Yes and no. One side says roll it and see who's dead. The other side kind of goes, this is really bad. Folks screaming in national daily newspapers about really bad stewardship of the route is kind of an impact in PR.
Two times they'll do that.
2 times?
Maybe 3. Because the first time they'll go, holy shit, what happened? The second time they'll go, God damn it, Joe, why didn't you fix that?
But you see the issues. There's a certain amount of care and attention.
David Farmer, University of Minnesota. In the higher education world, we do a lot of things with graduate students. And guess what? They graduate. And so there's all sorts of time bombs running around in there, in our infrastructures. And, well, this is a time bomb. The only thing that really concerns me isn't that there's going to be people that blow up, because that's going to happen, and that happens in the real world, and it's just going to happen. The thing that concerns me is we don't know how big the explosion will be. And that does give me a little pause. But the idea that we can do this without any pain is ludicrous. That there's going to be pain, we have to do that. But it's sometimes nice to know, are we talking about nuking a country, or are we talking about, a city or a block of a city,
I don't know, and you don't know, how many folk are behind resolvers with that behaviour who are not paying attention. And I can't find out, and you can't find out in the current technology universe.
Yep.
So you either alter the technology universe or just leap off the cliff. Chris? It's kind of saying leaping. And that's, one view, thinking, it's not that bad. The other view is, wow, dead is dead, that's really not good, we should be more careful. And that's the kind of argument that we're having. And it's a fine argument to have, because those are the two kinds of major issues out there. I wasn't following order, were you? Microphones?
Michael Sinatra, ESNet. I know there were people like maybe 3 or 4 years ago, maybe not 5 years ago, but there were people 3 or 4 years ago saying, if we're going to roll the key, let's roll it soon. Let's roll it as quickly as we can before DNSSEC really catches on. And I don't want to say I told you so, but I was one of those people, so that's how I know there were people doing it. But Warren already nodded; he was doing it too. The only other thing I want to ask is, does anyone who was involved in the early standards, so I remember Ed Lewis said something about this, about the idea of finding alternate trust anchor mechanisms, alternate chains of trust. And I suggested that we do something that was sort of bottom up to sort of complement the top down thing. That sounded an awful lot like DLV, and so everyone yelled at me. So, but what I'm thinking is a similar mechanism, definitely. Do we have alternate ideas about ways in which we essentially back up the root key so that if something goes horribly wrong with the root key, we don't turn off the internet? And is there any thought about that still happening, or is that too complicated?
If you read 5011, you find the concept of trusted keys going, quote, missing, quote. That you can announce a new key inside this whole concept and then withdraw it from the DNS key set. And recursive resolvers that are looking, who are good dogs, will leave it in their trusted key set. It's gone missing, but it's still trusted. And in fact, 5011 says you have to revoke it to get people not to trust it. So there is this concept that you can stack up trusted keys inside resolvers. But RFC 1435 says, I will only trust material that is inside this DNS key set signed by an RRC I trust. You can't just whip out a trusted key without any relationship to the current DNS key, signed DNS key set, and use it. It won't work. The validation standard says you can't. So either you change the validation standard, and the IETF does that really quickly these days, they're very good, or you find ways for resolvers to disclose which trust key you're using so that you can get folk to betray whether you're using a particular trust key or not, and see if that will give you a better metric of the cliff before you jump it. But, those are the kinds of options before us, yes.
Thanks, Jeff.
Warren
and or Tim.
Yeah. So I just wanted to point out that what Chris had suggested, was suggested a long time back, and Mike also hinted at that. It was suggested before the root was initially signed. It was also suggested by Steve Crocker in the last 2013 recommendation, but there was no follow-up from that ever. And the reason I mention it is I'm kind of concerned that we might end up in the same boat again, where there's a bunch of recommendations that just don't get followed up on.
I would hope that this effort leads somewhere, Warren, rather than just shelving it. I really would. We have to do something.
So, I'm Tim April from Akamai, not speaking for them. So speaking as one of the former grad students that Dave was talking about, I pushed hard for them to actually use the trusted key stuff, and most people never accepted it. So I'm totally for rolling it now, especially with now FISMA requiring the government domains to be DNSSEC signed. So people are starting to do DNSSEC. We might as well rip the Band-Aid off now before everyone's everyone's validating, and actually the internet goes dark.
By the way, this one now requires validation also. also not just signing for government domains. It's just a real.
And I would expect PCI to be not too far behind on that one.
It would help, both of you, all of you, it would help to tell us something, even if it's a one-liner. It really would. Because at the moment it's kind of guesswork in the dark by a small bunch of people. The more input you have into it, the more we kind of feel with confidence that there is some, you know, evidence and reason to take a particular choice. Choices will have to be made, and, you know, there is this issue that if we roll now, we've got a problem. If we defer, like Warren says, we can argue for defer for lifetimes. We're really, really good at that, and maybe that's a bad thing too. So, you know, your views would be helpful. And there's no others at the microphone. Thank you.
So thank you everyone for coming to the DNS Track. We will see you at the social tonight and around the next few days.